Optimization. For optimization, we're going to be using a maxima for maximizing and a minima for minimizing an independent variable. Objective. Number one, model real-world projects using algebraic functions and possibly trigonometric functions. Find the maxima or minima from the differentials of the functions. Apply the test to ensure the existence of a maxima or minima. Use the maxima or minima that meets the conditions of the real-world project. How to use calculus for optimizing engineering projects. Have a hand on the project. Develop mathematical exemplary for the problem if possible. Sketch a graph for the resulting mathematical equation. If you are able to identify the intended extrema by inspection, you're done. Otherwise, if the equation represents a function, then find the critical points. Check each critical point for the intended extrema, whether you're looking for a maxima or minima. If any of the critical points matches the intended extrema, you're done. Otherwise, wait until you take more optimization courses. Suppose that you're about to optimize the following. Your task is to fence the backyard of the engineering building. So our task is to fence the backyard of the engineering building. Here is an abstraction of the building. The building is in blue and the background is outlined using the green broken line. In blue, rectangular shape is the building, and this is the fence that is supposed to be built. And the fence, only 3 sides we need to build to cover the area. So, project, your task is to fence the largest possible area using 40-meter fencing material. So we have the material enough for 40 meters circumference if you wish. And however way we could do it in a round shape, we could do it in a rectangular shape, we could do it in square shape, whatever shape, but we want the maximum area possible with the limited material for the fencing, which includes 3 sides. Like I said, it could be a half circle, it could be a square, whatever it is, could be a triangle, whatever it is, it should just give us the largest area. That is our aim. Now it's time for us to apply the basics of the calculus that we learned to a real world problem. And this is like a project if you wish. And what we need to do is we need to decide the type or shape that we could use to get a maximum area out of a fence that is about 40 units long. So we have this as the background of this building, and of course we're not going to fence the wall of the building. We're going to fence the open area. So we have 2 sides to be fenced, and these are like the width, and 1 side is the length. So we have 3 sides. So let's take it one step at a time. The fence should cover 1 length and 2 widths of the broken lines, assuming that the broken lines are just lines that will identify in 2 variables, x as the width and L as the length. And then we will use these 2 variables to determine what kind of shape will give us the largest area. It could be half a circle, it could be a square, it could be a triangle, but whatever it is, we're going to figure it out in a minute. So like I said, The fence should cover one length and two widths of the broken line. So if we let W to be the width and assign X to be the length, the width itself, if we assign X for the width, it follows that L, which is the length, is equal to 40 minus 2X. The reason being, the length of the wall should be 40. And since this is X and this is X, then 40 minus X will give us the length. So L is equal to 40 minus 2X. This implies we can also represent it as L of X, L as a function of X, equal to 40 minus 2X. That's our first equation. We need another equation because we have two variables. And the second equation, we can get it from the area. The area is now, it's identified by the broken lines. The area will be the width times the length. That's going to give us this area. So let's go ahead and record that. So the area A, as identified by the fence, is A of X, that means A is a function of X, equal to X, which is the width, times 40 minus 2L, which is the length. And that's going to give us 40X minus 2X squared. So now we have modeled what we want in terms of an equation. Now we have to go ahead and find out the maxima if there is one. But before that, we have to find the critical points. So to find the critical points, we have to do the derivative of A of X. So like we said here over here, the derivative of A of X, which is equal to A prime of X, is going to be equal to 40, the X will drop, minus 4X. And since we want to identify the critical points, we have to equate the derivative to 0. So 40 minus 4X equals 0 implies X is equal to 10. To prove that 10 is indeed a maxima, and to do so, we have to check either through A and make sure that if we plug in 10 here, then the value that results from plugging 10 will be greater than the value that we will find for 9 and for 11, which are the two closest points to 10, if we're assuming only whole numbers. Now, so the next step is to go ahead and figure out the area given when X is equal to 10. Check 10 if a maxima, assuming that the aim is to maximize the area. So A of 10 will be equal to 40 times 10, that's 400 right here, minus 2 times 10 squared, that means 2 times 100, which is 200. So 40 minus 200 equal to 200. So the area is going to be 200 if we took X equal to 10. If we consider X equal to 9, the area is going to be 198, because 9 times 40 is 360, and then 2 times 81, because X is 9, so X squared is 81. 2 times 81 is 162. Difference is 198. So to the left of 10 is 9. The value of the function is less. Let's take a look at to the right of 10. A of 11. A of 11 is going to give us what? 40 times 11, that's 440, minus 2 times 121. So that's going to give us 242. That's equals to 198. But A sub 10 is greater than A sub 9 and greater than A sub 11. So it must be a maxima. We can prove that it's maxima also if we go through A prime. So let's take a look at A prime. So A prime of 9 is going to be equal to 40 minus 36, because we just plug in 9 here. So 40 minus 36 is going to give us a positive number. So to the left of 10 is a positive number. Needless to mention that if we plug in 10, we're going to get 0. So a prime of 10 is equal to 40 minus 40 is equal to 0. So to the left, a prime of 9 is going to give us 40 minus 36, which is a positive number, 4. Let's take a look at a prime of 11. A prime of 11 is going to be equal to 40 minus 44, because a prime is 40 minus 4x. So 40 minus 44 is equal to minus 4, which is negative. So since to the left of A10 is positive and to the right of A10 is negative, then we know that the point 10 is actually a maxima. Why? Because the curve increases, the slope increases, and that's positive slope until the slope becomes 0 at 10, and then the slope will start getting negative slope. So positive slope before 10, 10 slope 0, after 10 slope negative. So this is a maxima. And this proves what we want, and that's it for this one. Let's tackle another. This is an example that's similar to the one we just finished, but the only difference is that this example considers all 4 sides of a rectangle. So let's take a look at the example and go through its solution. The example states, find the maximum area that can be fenced by a wall to be built using 40 blocks of wood, 40 lumbers, each having a width of 1 meter. The area must be built using all the 40 blocks. We cannot leave out any block, we cannot add any block, we cannot use half of a block. We have to use all the blocks as they are to build an area as maximum as possible. So here is what we should do. Let the width be and the length as follows: W for width and L for length respectively. Since we have 2 unknowns, we must find 2 equations involving W and L. Obviously, since we are having W and L, width and length, then we're talking about either rectangle or we're talking about square. So let's go ahead and see if that's going to work for us. Now, we can use the given circumference of 40. So since 40 must be the circumference and we have to build 2 widths and 2 lengths, then 40 must be equal to 2W plus 2L, and that makes 20 equal to W plus L is our first equation. Therefore, we can solve for L, so L will be equal to 20 minus W. Now we have to go for the second equation. We could use the area as a second equation. So the area equals to the width times the length. This is the area, so we can replace the length, which we said it's equal to 20 minus W, so the area will be W, but instead of L, we multiply that by 20 minus W. That's going to give us 20W minus W squared. Now, since we have the area, now we have to figure out if we can find a solution for this equation where W should be giving us the maximum area possible. And to do that, we have to get the derivative of A, or we could just go ahead and keep plugging until we figure out the area when we figure out the critical points. So the critical points will tell us exactly where we're going and how we're going to find the maxima, and in that case, if there is a minima also, we will try to find. So doing the derivative will lead us to the critical point, which is a point with a slope equal to 0. But that point could be a maxima, a minima, or inflection point. So we will see what it is. So let's go ahead and take the derivative. So A prime is going to equal to 20 minus 2W, which is right here, 20 minus 2W. Since we want to find the critical points, we have to make A prime equal to 0. That means 20 minus 2w equal to 0 implies w equal to 10. So now that w equal to 10, let's see if 10 is a maxima or a minima. Therefore, the critical point 10 is either a maxima or minima or inflection point. So to figure out if it is a maxima or minima, we could use the derivative and see the slope before 10 and after 10, and we're going to go before 10 by 1 point and after 10 by 1 point. We're going to use only the whole numbers. We're not going to use fractions. So therefore, the critical point 10 is either a maxima or minima or inflection point. So we have to plug in for a of x. A is a function of x. We have to plug w equal to 10 in this equation, which is 20 minus 2w. We have to plug in w equal to 10. If we do so, it's going to give us a prime equal to 0, which is what we want. But we want also to have a prime of 9. So a prime of 9 is equal to 20 minus 18, which is equal to 2. And a prime of 11 equal to 20 minus 22, which is equal to minus 2. Now we can see that when we move from 9, at 9 the slope is positive, and then when we move at 0 the slope is flat, 0, and then we moved past 10 to 11 the slope became negative. So the slope is going positive and then 0 at 10 and then goes negative. So that implies that it is a maxima. W equal 10 will give us a maxima, and the area, which is a of 10, is going to be equal to 200 minus 100. You just plug in here for the area. 20 times 10, that's 200, minus 10 squared, that's 100. That's going to give us the area of 100. So 100 is the maximum area that we can get out of the 40 blocks. And obviously, that is the maximum area we can get. Let's take a look at the minimum area we can get. Since we cannot use half a block, that means if we want the minimum width could be equal to 1. So let's try to figure out the area and the circumference when we have w equal 1. So to find the minimum area, let w be the minimum width, which is 1. It follows that L will be 19 because twice the width is 2. Minus 40 is 38. Divided by 2 is 19. So the length will be 19. So while the circumference is twice the length, which is 2 times 19, plus twice the width, which is 1 times 2, and that's going to give us 40, then we can see that the area of the fence when the width is equal to 1 is going to be only 19, because it is 1 for the width and then 19 for the length. So 1 times 19 equal to 19. So this is the minimum area, 19, and the maximum area is 100. That's it for this one. Let's take a look at another example. This is the nice example. For this example, we have to optimize the cost for a building that has or supposed to have 10,000 cubic meters as a space. So let's go ahead and follow the steps that are necessary for achieving what is required. To optimize the cost, we need to find the maxima for the independent variable that will meet the desired space. Assume the shape of the building is cylindrical with radius r and height h. We need to find two equations involving the two variables. The first is for the space and the second is for the building material, which includes the circular wall, which is the outer wall, from the ground all the way to the roof. The circular wall, the roof, which is the material used to cover the building from the top, and the floor. The space S is given by pi r square h, which equals to supposed to be equals to 10,000 cubic meters. So this can represent our first equation. Building material for the roof, because the roof is like a circle, so the area of the circle is pi r square. The floor also has the same area. We're assuming the cost for both of them are equal. And the wall could be given by 2 pi r, which is the circumference, and then multiplied by the height, and that will give us the wall, the material for the wall. Pi r square h, which is the space for the building. So the space for the building is pi r square equal to 10,000. That's our first equation. Our second equation is the building material. Capital M equal to 2 pi r square, where 2 pi r square refers to the roof and the floor. And like I said, the cost for the roof and the floor are the same, and that's why we're adding them together. So 2 pi r square plus 2 pi r multiplied by h. 2 pi r square is for the roof and the floor, where 2 pi r is giving us the circumference and h will give us the height. So these are the two equations. We have to solve these two equations, and we have to look for the values of the independent variable, which is r, that give us m, which is the material, and we want to reduce the cost for the material, and we want to keep the area 10,000 cubic meters. So let's see if we can get that one. From the first equation, we conclude that h equal to 10,000 over pi r square. The second equation is m equal to 2 pi r square plus 2 pi r h. Now we can evaluate m using the value of h. So we plug in the value of h, which is this one. We plug it over here instead. So if we plug in that value, we get m equal to twice pi r square plus 2 pi r. Instead of the h, we're going to replace it by its value, which is 10,000 divided by pi r square. Therefore, m is equal to 2 pi r square plus 20,000 divided by r. To find the critical point, we need to find the derivative of m. So derivative of m is going to give us 4 pi r minus 20,000 divided by r square. And we have to equate it to 0 to find the critical points. And if we do so, we will find pi r cube equal to 5,000 root. So that's what we're going to get. So r is equal to the cubic root of 5,000 divided by pi. That's going to give us about 11.68 meters. That's the radius of the building. Since m prime evaluated at 11 is going to give us 4 times pi times the value of r, which is 11, minus 20,000 over the value of r square, which is 121, is going to give us 138.25 minus 165.3, and that is negative. That means the slope is negative at r equal to 11. Let's take a look at r equal to 12. M prime of 12 equals 250.8 minus 138.9, that's greater than 0. So we conclude that the slope is, in this case over here, the slope we can see is negative slope, and then at 12 the slope is positive. In between the slope is 0, because the slope for r equal to 11.68 8 is 0. So the slope starts from negative and then it becomes 0 and then it becomes positive. What does that mean? That means that the point where r is equal to 11.68 is a minima. And if that point is a minima, that means we're minimizing the material for the building. And that's what we want. We want to minimize the material for the building while achieving the maximum area, which is 10,000 cubic meters. That's it for this one. This problem is really a practical problem. It's about placing a building nearby an airport with certain constraints. So let's take a look at the constraints and see what we have. This is the definition of the project. Your task is to plan the most spacious cylindrical building between a cuboid building. So let's take a look at, this is a cuboid building and a road. And this is the road. The road is about 60 meters away from the cuboid building as shown in the figure. So this is 60 meters, this is the road, this is the cuboid building, 60 meters. We want to place a cylindrical building between them. Since the building is near the runway of an airport, okay, so there will be an airport over here to the right of this road, okay, and landing planes will descend to 30 meters altitude. That means there will be 30 meters altitude. That is the line for the landing plane. So that means the building cannot be 30 meters. It should be less than 30 meters to keep a buffer of safety. So we have to find the optimal radius for the building. So to design such a building, first of all, we have to put a triangle. And the triangle is going to be something like this. The base of the triangle is obviously 60, but we want the height of the triangle to be 30. So if the base is equal to 60 and the height is equal to 30, now we want to squeeze the cylindrical building inside this triangle. So that's what we're going to do. Now that we put the building inside, now we're going to go ahead and look at the parameters of the cylindrical building. First, R is radius of the building, and then H, which is the height of the building, and then B, which is the buffer. So the buffer, now since we said that the planes will be flying on an altitude of 30 meters, that means H plus B is 30 meters. So this is the distance. H plus B is 30 meters, where H is the height of the building and B is the buffer area. That's the safety area, because even for some reason, if the plane is flying not at 30 meters, at 29 meters or 26 meters, it will still be safe while it's landing. So now let's go ahead. We have two variables now, R and H. We want to somehow optimize the space. That means we want the largest space possible fit under all these constraints. So let's define this angle as theta. And of course, this is 90 degrees angle. So if this is theta, this also is theta. We have the larger triangle, which is half of the bigger triangle. And then we have a smaller triangle over here. So theta, tan theta is going to be equal to B plus H over 30, because this is half the distance. So tan theta is equal to B plus H over 30. But we know B plus H is equal to 30. So tan theta is equal to 30 divided by 30. So tan theta is going to give us 1. But also, this is theta. So tan theta for this small triangle, tan theta is going to be the opposite, which is B. But we can get B by subtracting H from 30. So 30 minus H divided by R is going to give us tan theta also. So we can say that 1 is equal to 30 minus H over R. And then we can cross multiply and that will give us 30 minus h equal to r, and that implies h equal to 30 minus r. That's equation number 2. Equation number 1 is about the space. So the space S of the building is going to be pi r square times h. Pi r square is the area of the circle times h. That's going to give us the volume, which is the space. So from this equation, S equal to pi r square h, we can solve for h. So h will be equal to S over pi r square. This is the first equation. And the second equation gave us h equal to 30 minus r. Now we have to plug in the value of h over here. And that's what we're going to be doing next. So equation 1 implies h is equal to S over pi r square. Plugging in the value of h in equation 2, we get S over pi r square equal to 30 minus r. If we cross multiply, we get S equal to 30 pi r square minus pi r cubed. Now to optimize the space in the building, we have to first of all get the derivative of S, and then if we get the derivative of S, is going to be equal to, it will be 60 pi r minus 3 pi r square. If we equate it equal to 0 to find the critical points, we'll find that r square is equal to r square minus 20r equal to 0. So r is equal to 0 or r is equal to 20. So to show that r equal to 20 results in the maximum value for S, we need to first find S prime of r for r equal to 19 and for r equal to 20. And if we do so, we have to plug in 19 for r. So 19 square multiplied by 3 pi, and over here 19 multiplied by 60 pi. And if we do the math, this is 19 multiplied by pi multiplied by 60, and then this is over here 10,083 is 3 multiplied by pi multiplied by r square, and this is positive. If we look at S prime evaluated at 21, that means we will plug in for r 21 and over here for r 21 square, and that will give us 1268 minus 1323, and this is less than 0. So we can see that for 19 the slope is positive, and for 21 the slope is negative. In between, for 20 the slope is 0. So this must be a maxima, and since this is a maxima, it guarantees that we're going to get the maximum space for the building. And that ends this problem, and thank you for watching. You have a good day.